Am I speaking? Oh, I'm sorry, everyone. I wanted to say thank you to Daniel and the other two panelists and apologize for the technical issue with Jasek's presentation. Our last panel for today will be looking at how biochar production and use is being used to adapt to the increased vagaries and vicissitudes of our climate. USBI Executive Director Tom Miles, who I'm guessing most, if not all of you know or have heard of at least, will be moderating this panel. As John Webster mentioned yesterday, Tom has been doing yeoman's work for more than a decade. He's helped so many companies and individuals to find their way in this industry. Included in this panel will be a discussion on how biochar can help with stormwater management, how it is able to provide some relief with increasingly salty soils, and how in future it may be able to help with post-disaster recovery. So Tom, I'm passing things over to you.
Okay, thank you, Kathleen, and thanks for the opportunity to present this panel, Biochar and Climate Adaptation, Loss and Damage. We have three great panelists. The first panelist we'll start with is Chuck Hegberg. Worked with Chuck for a number of years now, concentrating on stormwater activities. He's been intimately involved in a lot of the research and development having to do with the use of biochar and application in stormwater. Chuck?
Thank you, Tom. I'm assuming they can get my slides up here. My head's going to be bouncing back and forth. I got a dual monitor, so I've got the slides in one eye and my notes on the other. So if I'm bobbing around, that's a good reason. Well, thanks for everyone for joining this talk. As we know, we're in this process of trying to scale up the biochar markets and to be able to look at ways to abate or adapt to climate crisis that we're dealing with. And nature-based carbon solutions for stormwater, I think, has a huge opportunity for us. So this presentation hopefully will help you take a peek under the hood of stormwater management and how biochar can be significant market player. So for this presentation, the flow of the presentation will be first that I'll be framing out the climate stormwater challenge. We'll then discuss nature-based solutions for stormwater management. And then lastly, provide some practical field data on biochar's enhancement to nature-based solutions or green infrastructure. Next slide. Little delays there, but anyway, from a climate change is actually, I guess you can say, laying bare our anthropogenic impacts or our past sins or existing ones, putting urban infrastructure and populations into extremely vulnerable situations, including water security, water pollution, food security, human health, and disaster risk management. We need to adapt and retrofit our cities quickly. The potential to stack, and that's an important point, stack nature-based solutions linked to the growing conservation finance markets represent a tremendous opportunity to address urban climate change, and not just carbon sequestration, but water storage, water quality, flood reduction, and so on. Next slide, please. In most parts of the world, we're starting behind the eight ball on managing stormwater. So doubling our urban population in the next 25 years is going to be more daunting of a task. And then those numbers are moving into the 9 billion population, or 7 of every 10 people living in cities from the World Bank, is going to really make the challenge even more difficult. Thankfully, there are countries starting to develop national programs to address the challenge, including China's sponge cities, the Nordic regions with their focus on living streets, and then the more recent U.S. federal nature-based solutions roadmap for National Carbon Task Force. And before I forget, what I'm going to do is I'm going to drop that link. Let me see if I can do that in there, because I didn't have it in my talk, but there's a link to that new document that just came out in November. Next slide, please. So just for those that aren't familiar with green infrastructure or nature-based solutions, the definition of a nature-based solution refers to actions taken to protect, sustainably manage, or restore natural or modified ecosystems to address societal changes. simultaneously providing benefits for people and the environment. Nature-based solutions often come at a lower cost than traditional infrastructure, and commonly called NBS is also referred to as green infrastructure, natural infrastructure, and natural and nature-based features. For green infrastructure, I do have the definition up there, is to focus on the management of stormwater runoff using natural ecosystems and or engineered systems to mimic natural systems. Next slide, please. Now, there's a lot of information going on here, and I don't mean to overwhelm you with it. You will obviously be getting copies of this so you can dig into it deeper. But basically, what this is showing is there is a spectrum of nature-based solutions in green infrastructure. Obviously, as we increase the impervious area of our landscapes, the costs associated with dealing with those from constructed wetlands or stream restoration or agricultural soil health programs in scenario A, all the way up to some of the work that we're seeing in Stockholm and so on the highly impervious built out cities become very, very expensive. And but all those, with the exception, each treatment area of impervious area increases rapidly, the cost associated with that. The key to nature-based solutions is to increase the hydrology lag time, meaning infiltration, retention, and storage, in a distributed manner in order to disrupt the hydraulic time of concentration within a drainage area. So in other words, slowing down the point of when water all joins together and creates catastrophic flooding, slowing it down to allow for water quality benefits to occur, and to store it in the soils rather than generally running it off. Also, as a note, just because it's green doesn't mean it's functional. Developed green can act more like impervious area than natural spaces. You go to the next slide, please. So obviously, I'm going to focus more on the U.S. here, but I'm sure that these numbers are going to be probably fairly similar from around the world in developed countries. But in the U.S., we enjoy our artifacts of the English garden and religiously tend to our lawns. It is a fact that turf or lawns are the largest agricultural crop. We have nearly 28 million acres of impervious cover and over 40 million acres of lawn and turf. There is a tremendous opportunity to use nature-based carbon solutions to convert these areas into functional stormwater management systems at a fraction of the cost of traditional stormwater management and gray infrastructure systems. And on top of that, of course, as we're improving the stormwater capacity of these green spaces, we're also able to tap into carbon sequestration and the other benefits there. Next slide, please. One other point I wanted to make on that last slide was that currently the US EPA is estimating that it costs us about $300,000 per impervious acre that we're treating, which is an enormous number. When you think about the 28 million acres that we have, how much we're going to have to address. On this slide, this one is focused on looking at how much area, if we're going to convert areas, that we need to treat in order to start seeing any meaningful modifications. And this is looking at both a watershed and a site basis. The data that I'm going to provide to you from this research, which obviously I've provided the references to, does not include the use of biochar, and that's an important point. So the secret sauce here is that we don't have to treat all the green. Obviously, in a carbon sequestration world, if we want to treat all that green, we can to just have an urban soil health or other things. But as it relates to stormwater management, the studies are indicating a target of about 15% of the underutilized pervious areas are what you want to target. They will provide the greatest value, especially when placed along streets like they're doing in Stockholm, to reduce peak flows for smaller events and maximize floodplain storage for flood protection. Doing more doesn't necessarily mean better. For small storms, a spatial location is more important than the number of facilities or best management practices, green infrastructure practices that you put in the watershed. For on-site practices, and that's the middle image here, is the red circles and our demarcation points. It's the hotspot disconnections with soil compaction and amendments resulting in a greater than 64% reduction in runoff. Holistic intervention as a synergistic effect, 2 times more effect on reducing surface runoff and increasing deep drainage and evaporation. And you can see that on the graph right here on the GI treatment effects and benefits, the left-hand bar there. What it's saying in that statement is that when you basically combine different types of techniques, not only do you get those benefits, but you actually get a synergistic effect to it, with the increase of deep drainage and evapotranspiration. The effect basically is a 6 to 17 times more effective amending soils at the pervious interface than amending the entire yard, which is those areas that I've identified in red. Manipulating the interactions at some parcels or within the watershed can be compensated for other areas where infiltration remains reduced or limited. Essentially, we can basically model the watershed and say, if we can't put amendments in soils or modify and add green infrastructures to certain location because of constraints, you can offset it by targeting different other areas. So let's go to the next slide and take a look at the benefits of biochar when applied to nature-based solutions. This slide here is some work that I was doing in partnership with the University of Delaware. It was essentially, we were looking at modifying what we call bioretention media. It's an engineered media, primarily of sand. It could have fines and sawdust and other aspects to it. But what we ended up doing was modifying a number of different states' standards. Every state sort of has their own bioretention mix standard. And we went ahead and modified a few of those. And what you see here on the lower right is the leachate that came through based off each of the types of bioretention media. So basically what we have is that we retained about 27% more stormwater. We had a higher redox. We had infiltration rates increased 4 times, less clogging, and improved plant health. Can we go to the next slide, please? And here, I'll skip these for the sake of time, but here are a number of green infrastructure that would be considered type of treatments that would use an engineered media. Next slide, please. The other part of the work being done is in situ soil remediation. Similar to agricultural soil health, in situ amendments in urban soils to address stormwater management is a golden opportunity. There is a tremendous amount of underutilized green space that can be easily retrofitted to stack nature-based functions, including stormwater management for both small and large events, water quality, and carbon sequestration. As every site is different, this approach is more complex than the development of a biochar-enhanced bioretention media. Next slide, please. Again, a lot here, but to summarize this, basically, we amended the soils with biochar, and what our goal was to better improve the infiltration and storage capacity was to shift the hydrologic soil group function by changing the aggregate or the characteristics of the soil from a D and C group to a B or A group. On top of that, what we were able to get was that we were able to get the intraporosity and the interporosity functionality going with the soils when we amended it. One of the facts that we have found with this is that when you put biochar in, and you can see from the irregular shape of the wood biochar, when you add biochar to it, it acts like an aggregate. And then once you shift it from an anaerobic condition to aerobic condition, soil microbes take over and you begin the soil aggregation process. Next slide, please. Here is just showing how much water runoff that we were able to reduce on the for the stormwater runoff here. Let me switch panel here. The treatment, basically we were able to reduce 53% runoff from a single storm, but over the life of the project, we actually had an 88% reduction of highway runoff by the soil amended with biochar. Yes. The other aspect too was that we improved infiltration, and over time it began, the tilled section began to recompact, while the biochar amended sections did not. Next slide, please. This slide is basically showing how consistently biochar at the up to 15 centimeters and then up to 30 centimeters basically increased water holding capacity of the soils once they were amended. So up to 15%, we had an 83% increase, and then up to 30 centimeters, we had a 50% increase. So you can see over the control, it's very, very consistent through the whole process. Next slide, please. And lastly, on the data, one of the things from that increased water holding capacity was the moderating of soil temperatures. And this was over the life of the project. This is only a small snippet of it. But you can see that the blue lines are the unamended soils and how they are very, there's my time, that they're very extreme. And whereas the biochar amended soils were metered very nicely. So what we found was it was cooler in the summer. The soils were warmer in the winter. They were, and then there was also that less wild extreme shifts, which is critical for microbes and continuing nutrient reduction. And the last slide is just sort of a summary of it. I've already touched on a number of points here, but the takeaway is that in the next 25 years, we're going to have built 9 billion people living in our urban centers, which means we're going to have to expand and be able to deal with that, and of course, increased runoff. Governments are moving too slowly. So like the carbon markets, the private sector needs to jump in. There should be, when you're dealing with flooding and water quality issues, potential to work with insurance companies. Obviously, flood reduction plus climate adaptation equals money when it comes to property and life, catastrophic life payouts. And then addressing urban stormwater provides many cost-effective, long-term nature-based carbon solutions. And the O&M, one of the things we're finding is obviously O&M costs are driven by inflationary costs, and there's far less necessary. Plus, as the slide is showing, we can actually do the same treatments in a much smaller footprint because of the function of biochar. So I'm a few minutes over, so I'm going to turn it back over, and then we can address questions and answers, I guess, later. Right, Tom?
Good. Yes, thank you, Chuck. And Chuck has shown us how there are many ways in which we can use biochar to manage our normal stormwater issues. Next, we have Dr. Jonathan Sherman, Forestry Coordinator of the Office of Net Zero at the province of Prince Edward Island. And Jonathan is going to talk to us about how biochar might be used to recover from these climate events that we have. Jonathan?
Hello. Thanks for having me. I'm going to have a pretty quick slideshow today, so I think that's hope that suits everybody. Great. Yes, and thanks Chuck for the great talk. Okay, so biochar for disaster relief. Here we are up here on Prince Edward Island. Why don't we just go to the next slide right away here? Yes. Okay, so here I am on a mighty little Prince Edward Island, just for a little bit of context of where I'm coming from, because I've been in my capacity as a civil servant working on Prince Edward Island's net zero 2040 strategy, specifically in the forestry and land use department. So for the sake of PEI is kind of small, so you want to kind of get your scale bar out and kind of adjust a lot of the figures that we're talking about here. But I'm going to tell a little bit of the story of what we were thinking biochar, how we were thinking biochar could integrate into our climate change mitigation strategy. And due to a sort of climate change exacerbated natural disturbance in late September, now kind of pivoting towards that as an adaptation, as a kind of a hybrid adaptation avenue, which would certainly fall into the category of building the plane as we're flying it, as you'll see by the end of the presentation. But PEI, so Prince Edward Island, PEI, is Canada's smallest province, island jurisdiction in the Atlantic coast. It's about 5,500 kilometers squared. So it's very similar in size to the state of Delaware for the American-centric audiences out there. We are very heavily agronomized. 42% of our province is agricultural land, and about 45% of it is forested, and that's on the decline. So we are hemorrhaging forest cover, and a large component of my role here is trying to figure out ways that we can hold on to that. And I'll get into some of our forest cover stats. And at a population of approximately 160,000 people and growing, we're Canada's most densely populated province. And it's interesting data that I was able to pull out is that we also have the highest road length per land area ratio of any Canadian province. So we're twice as road dense as Nova Scotia, 5 times as road dense as Ontario, and 10 times as road dense as Quebec. So that will be relevant information for when we start talking about the high cost of the climate change calamity that impacted us in just a couple months ago. So next slide, please. Right. So we are Canada's most densely populated province. Space is naturally quite precious here. Right. And so you can see our forest cover stats there, and I'll just get you to flip. There should be a population growth. Next slide, please. There should be a little, this population. So we can kind of see here how our forest cover and population growth stats have kind of fluctuated in unison through time. So we kind of had a mini population boom in 19th century. Something of a population collapse about 100 years ago, and we've been steadily increasing. And now that we're on this sort of uptick of increasing, you can see in the bars on the left there, we're losing forest. So next slide, please. So because we've had kind of a large recovery in forest cover, but in a relatively unmanaged and poorly planned way. And we've been using sort of forest management techniques that are not very suited to the eastern temperate zone, but much more suited to a kind of a northern boreal zone. And a lot of the forest so we've been clear cutting kind of willy-nilly. It's fair enough to say that Prince Edward Island has a failed forestry industry and forest resource planning strategy. So as a result, we have a kind of a massive cohort of essentially energy grade or biomass grade material. And so we're kind of in the situation where we've been needing to jump through the hoop of rebuilding a forestry industry around sustainable biomass offtake. So next slide, please. I hope this isn't too small for people, but this is just a recent forest data demonstrating about 75% of our timber holding is sub-lumber grade. And so we have about 15 million tons of biomass grade material with something which we need to do something with. So next slide, please. So this is just painting the picture a little bit of how biochar was looking to fit into our climate change mitigation strategy, and I'll get to the kind of adaptation part in a second. So we're also in the midst of a soil carbon crisis here on Prince Edward Island. Prince Edward Island, being Canada's smallest province, produces more potatoes than any other Canadian province. And so generation by generation of farmer, we've really been working soils very hard. And so we have sandy, overworked, acidic, low cation exchange capacity soils. And many of our soils are kind of at the brink of collapse because of this loss of organic matter. And so we have a massive we have quite a lot of room in our soils to bolster soil carbon uptake. Next slide, please. Right. Okay. So you just look at maps of Canada's room for soil carbon sequestration in agricultural systems, and we're high to very high across the board. So many potato farmers are getting quite desperate, and biochar is an option to kind of hack soil organic matter restoration is increasingly appealing. It's appealing across all industrial sectors, not just potato. So next slide, please. And so I think members of the biochar Illuminati that we have aggregated today will kind of see how biochar fits nicely in the Venn diagram of needing to reboot a forest industry around sustainable biomass offtake and needing to launch large-scale regenerative agriculture projects. So that's kind of the case up until about September 22nd. So next slide, please. And then that sort of nicely, that strategy was which was kind of coming together nicely, one brick at a time, was turned upside down quite quickly by Hurricane Fiona, downgraded to Tropical Storm Fiona by the time it reached Atlantic Canada. But you can see, if you can kind of think back to that original slide and pinpoint where Prince Edward Island is, you can see that although it was curling out into the Atlantic, it took a hard left turn and really hammered Atlantic Canada, and especially eastern Prince Edward Island and southwestern Newfoundland, which is that larger island right above where you see SAT there Saturday. So next slide, please. So the impact was really devastating. So this is the most severe storm that has ever impacted Prince Edward Island. We have caught the tail end of lots of hurricanes downgraded into tropical storms before. 3 years ago, we had Hurricane Dorian, which was also the worst storm that most people remember. The difference being that there were lots of, after Dorian, there were lots of sites that you see here, except for the sites that you're seeing here are all over Prince Edward Island. So the top left and bottom right, you can see. So the bottom right was out my balcony, it was across the street outside my balcony the next morning. Had most of Prince Edward Island's largest, most ancient trees are in Charlottetown, the capital city. We probably lost 75% of them, uprooted chunks of asphalt and concrete. And in the bottom left, you can actually see the impact of the storm on our dunescapes. And so you see that cloud of sand is actually the thousands of acres of sand dunes that we lost. And also on top of that, in the top right, just the many, many acres of just conventional forest cover that were lost. The main topic for today is going to be the top left and the bottom right, which is the emergency biomass cleanup from our urban areas and all of our roadways, which is why I kind of harped on that data point of Prince Edward Island having more kilometers of road per square kilometer than any other Canadian province. Next slide, please. Right. So now with the cleanup, there have been an array of Fiona biomass drop-off sites opened across Prince Edward Island. The rush has mostly subsided. Fortunately, private pit operators have stopped burying the material as they've come in, as we've sort of been able to apply the brakes on the conventional disposal options and buy us a little bit of time to do something a little bit more climate change strategic with all this material. But you can still drive around, and as you drive around, there are still, even though we have the drop-off sites, I mean, there is a giant pile of biomass on, at 5 minutes in any direction. If you walk 5 minutes in any direction, you're going to walk across a pretty large pile of biomass. So, let's go to the next slide, please. And of course, whenever you have people just heaping up piles of biomass, piles of fuel all over the place in urban centers and kind of rural pockets, One of the major concerns that's going to come up relatively quickly is fires. And so I was just walking around down by the Charlottetown Harbor, looking across the bay over to Stratford, and yes, a biomass pile had caught on fire and spread to an adjacent rec center, and that was another bolt on to the already injury of everybody losing all these feature trees is now fires and more property damage. So next slide, please. Okay, so just to give a little bit more scale to this. So what do we currently have, and what opportunities? Here's the lemonade. Here are the lemons. What lemonades can we make? What lemonade can we make? So we have 25,000 tons of material estimated at publicly run drop-off sites. Approximately, estimates vary, but at privately run drop-off sites, we have at least another 25 tons, possibly another 75,000 tons. So we'll just put that in the middle. Just for the sake of the big picture of how much biomass Prince Edward Island even has, and the big picture forest loss image. So Prince Edward Island has about 20 million tons of timber. That's in all of our forest land holdings. So for every 5% of forest cover that we lost, that's about 1 million tons of material. Estimates range from 5 to 20% of our forest cover has actually been blown over. And every million tons of material that we lost is 20 years of our current wood for energy consumption. So even if we're doubling our wood offtake capacity, we're really not making a dent in making strategic use of this material until we're kind of 10xing our offtake capacity. And this material does have a shelf life of maybe 2 to 5 years before we can actually use it for energy. So moving fast on this is kind of a priority. And next slide, please. So my thanks, my sincere thanks really goes out to Kathleen and the IBI, because I was able to reach out to them and very quickly get some excellent guidance on how we might be able to pivot our biomass disposal option and recover some costs by making biochar. So our current cost of processing these biomass, these are Canadian dollars, by the way. So it's about an American, so it's multiplied by 3 over 4 if you want to convert it into American dollars. But we're spending about $20 to $25 per ton to get rid of this stuff. That's grinding it and hauling it to a landfill. And there are an array of these different, essentially air-fed high-efficiency burn boxes. So Firebox is the green one, and thanks to Kathleen, I was able to follow a lead of contacts and track down a provider of these in Canada who has a number of used units, which we might be able to get here. And just this morning, a private operator called me and told me that he was interested in buying at least a couple of them. So we have a few of the jigsaw pieces have fallen into place, some more yet to be done if we want to potentially start banking carbon credits on carbonizing this material, which would be very helpful. But so these smaller units, they can go through about 7 tons of this material an hour. Conversion rate to biochar ballpark of 20%, and depending on how our LCA shakes out and how the LCA shakes out and how that whole accounting process goes, it looks like we can probably pay an operator to process material, end up with a little bit of money left over, and get all the biochar for free, which would be extremely useful at this time as we're booting up our biochar strategy. So next slide, please. And just a little bit of costing. People can kind of sanity check me on this if they think my figures are okay. But so let's say taking the middle of the road estimate of 50,000 tons of debris, 20% carbonization rate, lowballing our estimate of getting 2 corks per ton of biomass processed, and selling those at a market rate of 200 Canadian dollars per ton, which is maybe the most optimistic figure in there. So that's about $4 million of gross revenue for carbonizing this 50,000 tons of debris. plus we get about 10,000 tons of biochar for in that pile. And if we would be happy pivoting to this method of biomass disposal if we can undercut that $20 per ton. So if we can do it for $19.50, but that's the cost of disposing of that would be about $1 million. So the carbon credits are actually at the current rate of evaluation of the carbon credits, as long as I'm not being too greedy on that, still puts us well over the mark to deal with this in a more cost-effective manner. Now, that's notwithstanding the egregious amount of expenses that we encountered in order just to clean the material up. I mean, we were spending millions of dollars a week to get the material to these drop-off sites. So this isn't, this is in the context of cost recovery after a disaster. Next slide, please. So just a couple quick takeaways. So one of the important things that I learned after living through one of these experiences is it's not just the sort of, I mean, people lost a lot of value from their property. People, like, the damages were quite bad. People lost an insane amount of money. But as soon as people started realizing how much waste there was with all these trees going to landfills and not being sure if there was going to be anything sensible done with them, it was a real insult on top of injury just to the prospect. So there's also there's an incredibly important moral win here to pivot towards using the biomass more sensibly. Yes, it does look like the carbon credits can outweigh the costs that we have yet to encounter. So taking where we are now as the starting point, we can theoretically come out ahead and end up with a bunch of free biochar. If we can, this is kind of an ad campaign here right now to get in touch with biochar carbon credit project developers who are interested in perhaps exploring this with us, because that's the final piece of the puzzle. So come at me, but it's looking interesting, I think. And just a final nugget of wisdom is that I think it kind of behooves us to recognize that this is a disaster which was exacerbated by climate change. And so climate change adaptation and climate change disaster response solutions should probably strive to sprinkle a bit of climate change medicine into their approach. So I think biochar, as we are all firm believers in biochar, is climate change antidote. So we should be looking to sprinkle a little bit of climate change antidote in our response to all of these calamities. So thank you very much.
Very much. A lesson here, I think, is we need to get biochar into the conversation and into the planners ahead of time, ahead of these disasters, so that they're prepared for it. Very interesting application. So let's shift from PEI to kind of the opposite end of the continent, to New Mexico. Dr. Katie Brewer has been working for a lot of years with biochar in a number of applications. She's with the Department of Chemical and Materials Engineering at New Mexico State University, and will talk to us about biochar in saline soils. Katie?
All right, good morning, good afternoon, and good evening, depending on where you're tuning in from. So as my presentation loads, I want to tell you that we're going to shift a little bit from what most of you hear about and talk about arid and semi-arid soils, in particular, what happens to the salts. So next slide, please. So I'm going to give you a little bit about what makes semi-arid and arid soils different, the potential benefits and pitfalls of putting biochar on these soils, what we know so far, and then what needs to come next. So next slide, please. So for those who have not been to NMSU, this is us. We're in the Mesilla Valley of New Mexico. We're in part of the 4 deserts in the United States. We're at the kind of the northwestern side of the Chihuahuan Desert. So give you an idea of where we are. Next slide, please. But we're not alone in the world. There are a lot of semi-arid and arid lands throughout the world, and you can probably find yourself on the map and see that it's there. And so this represents about 1/6 of the world's population. And so this is a scenario that's going to impact a lot of people, even though it doesn't show up that much in biochar literature to date. So next slide, please. So what's the big deal? The biggest problem with desert soils is evapotranspiration, and this is how much water leaves the soil by either evaporating directly or going through the plant before it evaporates, that rate versus the precipitation rate. And this is a map taken from several years ago, but you can, if you downloaded this data at any given time of the US, you could see a map like this. And you can see New Mexico in the Southwest, and it's almost all yellow to red. And this means that at any given time of the year, our soils are losing more water than they are receiving. Why does this matter? When you have precipitation, it lands on our soils, and our soils are pretty young, and the water lands and it dissolves the minerals that are present. And that's perfectly fine in an area with enough water that water keeps moving downward. The problem with a fast evaporation rate is you have the water hit the soil, dissolve the salts that are there, and then evaporate, leaving these salts behind. And so you have this constant accumulation of salts in the upper layer of the soil, which is also where the plants like to be, and that creates some issues. And so if you want to know about arid regions, pay close attention to evapotranspiration versus precipitation. Next slide, please. So what issues does this cause? Well, there's three of them that I want you to take away from this, and these are unusual compared to any of the soils I'd worked with before. The areas I'd worked in before had plenty of rain, no irrigation even needed, and this had never come up. Now it's a big deal. And so the things that I worry about are salinity, SAR, which is sodium adsorption ratio, and the pH. So in a desert soil, it's more likely to be saline. This means it has an electrical conductivity greater than 4 decisiemens per meter. So you stick in your conductivity probe, and this is a number that you get. Most of our soils are neutral to alkaline. So in any given place, you can find 7.8, 8.4, those kinds of things. And this doesn't happen often, in New Mexico at least, but in other places of the world, you'll have a sodic soil. And this means that there is far too many sodium ions running around compared to calcium and magnesium ions. And this affects the structure of the soil, which can create many types of problems about water penetration, air movement, and generally bad for plants. And so when I'm introduced to a new desert soil, these are the first questions that I ask. What's the electrical conductivity of this soil? Is it saline? If it's saline, is it also sodic? And then what is the pH? So keep this in mind. Every soil we deal with in an arid region, we have to ask these questions. So next slide, please. So what could biochar do? Well, there's been some research, especially in the last few years, on biochars added to arid region soils. And what some of the benefits it can have, and Chuck mentioned one of these earlier, and that was affecting soil hydraulic conductivity, how easily water moves through soil. When you add char, it tends to move easier, which is good in a desert because that allows all of those soils that get dissolved in water to travel downward with the water outside of the root zone. This also helps reduce our amount of runoff if the water can go through the soil rather than over the top of it. Adding biochar adds the minerals that were present in the biomass, which is mostly calcium, magnesium, and potassium, things we want more of in the soil, compared to sodium, which we want less of. And so it changes the available ions. It's been shown in some of the studies that my group has done and some studies that other groups have done, it increases plant available water. So regardless of how much total water is in the soil, when you have biochar, more of it may be available to plants. And anytime you have more water available to plants, it reduces the amount of stress that they experience from the water that's present. Reduces soil bulk density, great for gas exchange, water exchange, root penetration, all of those things. And in general, there's been studies that have shown that plants tolerate salinity better in the presence of biochar. We don't know why, we have some ideas, but these are some potential biochar benefits. Now, next slide. As an engineer, I always have to think about the trade-offs. And many people have asked me, hey, we've got desert soils, they're low in organic matter, I should add biochar, right? And I give them the engineering answer. And anyone who's taken a class or listened to a talk from me before has probably heard my answer, which is it depends. And so if you're going to add a biochar, you have to be careful of these three things because we don't want to exacerbate those soil problems that I mentioned for desert soils. So some biochars, especially those from agricultural residues, can have a high ash content, which is perfect if you live in an area with an acidic soil. But that's not us. And so we have to worry about adding some of this alkali ash to our soils when it already has a high pH or relatively high pH. Then we have to worry about any sodium that might be in our biomass, because that sodium not only adds salinity to the soil, it also increases the risk of forming a sodic soil. And then high salt content, if our biochar is high in minerals, it may increase soil salinity by putting it on the soil. So our biochar may do wonderful things for carbon, but have negative impacts on the salt. So next slide, please. So as I said, there hasn't been a lot of research in this area, but I wanted to share some information about 2 studies that my group has helped out with to give you some idea of where this could go, and then kind of wrap it up with what we know so far. So the first experimental study was a what-if study. We had noticed that halophyte biomass, that's salt-loving plants, take up salt, and we wanted to know, could we remove salt from the soil using these plants and then trap it in a way that it's no longer plant available, it's no longer soluble, make it back into rocks, was the idea. So next slide, please. And this was inspired by literature that showed that when you have a biochar and you leach it with water, not all of the salts that are in the biochar come out. And so you're not meant to read this slide, mostly just to see that on the left side is how much salt was in the soil, and on the x-axis, how much time it was leached. And you can see that that number does not go to 0. So we know that some salt is trapped in the biochar during pyrolysis. And so the idea was, well, this happens. Can we do it on purpose? So next slide, please. So we found 2 of our local halophytes. This is Atriplex, better known as saltbush. So we got some of those samples. Next slide, please. Chopped it up. So this is the site where we collected it. This is in Alamogordo, New Mexico. We chopped it up, we dried it. Next slide, please. We put it through this was our 5-liter lab pyrolyzer. And we get our biochar and our bio-oil. Next slide, please. And then we did a series of studies. So in the upper left, you see a permiometer. This is where you put a sample into a tube and you gradually pass water through it. And we did that and collected the water that came out. So we knew how much of sodium, potassium, calcium, magnesium were in the biochar to begin with. And now we want to see how many of them come out. So we leached the soils and we're looking at short-term leachability. So next slide, please. And what did we learn? So from this whole study, which you can, it's been published, so it's accessible there, is we learned that some kinds of plants have more salt than others. No surprise there. The salt for these halophytes tends to get put into the leaves. And so if you're trying to trap salt, get the leaves more than the stems. When you make a biochar, the ability of biochar to retain the salt is limited. So it kept the salt in there for a while, but even after just 10 volumes worth of water, a lot of our sodium had already leached out. And so it can trap salt, but it's not very, very good at it. We also learned that pyrolysis temperature affects the leachability of the salts. And so it affects the carbon structure, which affects the interaction of the carbon with the minerals. And so it depends on temperature. And for our samples, we were able to hold on to more sodium best at lower pyrolysis temperatures. Next slide, please. So our second study, this was on agricultural soils. We grew some sorghum Sudan grass and some pinto beans, and we amended it with different levels of biochar, a high level and a low level, and we grew some crops. And this is after 4 years. We had switched the fields to study other crops, but in the meantime, we still checked on what were the impacts of those original biochar applications. So next slide, please. And I have 3 bits of data to show you. And the first of them is a thing that made us very excited. And this was that after 4 years, the highest level of biochar application still improved our soil's wet aggregate stability. That means the char forms bigger pieces and is less likely to blow away. We were very happy about that. Next slide, please. After 4 years, our biochar amendment had still increased the soil organic matter. And it looks like a small change, but every small change in a percentage can be a big deal for soil quality. So we're really excited about that. Next slide, please. And this last significant result, we were less excited about. So you can see on the left is electrical conductivity. And after 4 years, the soils where our biochars were applied did have significantly higher electrical conductivity. Now we're nowhere near the 4 decisiemens per meter. That would make it a saline soil. But what this told us is that even at non-saline soils, adding our biochar does increase the salinity, which over a long period of time or multiple applications might cause a problem. So next slide, please. So to summarize the observations of this 4-year field study, most of the biochar impacts were not significant after 4 years, but the ones that were seen at the higher rate of application, and they made us happy, except for the increase in salinity. Next slide, please. So what I want you to take away from this is that biochar does have potential to improve the salt situation in semi-arid and arid soils, as long as, second bullet point, we are careful. So we need to keep an eye on the soil salinity, the sodium adsorption ratio, and the pH. And as a researcher, I'm always going to say this, but in general, if we're going to make recommendations to our stakeholders, we need to know better about how biochars interact with the soils and the salts for these arid and semi-arid regions. And then we need to know what that changes in the plant, because just because the soil chemistry changes doesn't necessarily mean it will help or hurt the plants. And so we need to know both. So next slide, please. Some studies we currently have going on, and by the way, this is a picture of us terminating a run in our Ring of Fire kiln that we got last year to process pecan wood. We're very happy to get one of those. The 2 studies continuing is we have a study on the soil health effects of combining compost with biochars, different cover crops, and different tillage mechanisms. And then we recently have a study going on looking at the interactions of heavy metals with micronutrients in soils and biochars. So that's some stuff going on that we'll want to publish in the next year or so. So next slide, please. Some necessary acknowledgements, funding from multiple sources, many of them from the state, as well as the students and collaborators. Next slide, please. And then this is some follow-up contact information. And I included there John Edewu. He's in our Plant and Environmental Sciences department, and he's the one conducting many of these field studies that I've been collaborating with. So with that, I think we turn it over to general questions. Thank you.
Great presentation. I guess a question I have is, have you been comparing results with folks in other parts of the world, in the Middle East and so on, working in similar soils?
We need to start that. So I've noticed in the lit review for prepping for this presentation that especially in Western and Northwestern China, they've published a few studies in recent years. I have not looked as much into the ones in the Middle East, but that is something that I'd love to see a lit review specifically on biochar, salt, and soil. That needs to be done, whether it's done here or if someone else is actively working on it. I would love to connect to know what you've learned.
No, that's great. We get a lot of, at IBI, we get a lot of interest and inquiries from Pakistan, and also from the Middle Eastern countries and so on. So quite a lot of interest. Thank you. A question was asked of you. What's a high ash biochar in your mind for in a desert soil?
That is a loaded question. Partially because it depends on what kind of ash it is. If it's a high silica ash, like you would find in corn or rice, it doesn't really matter. That silica does not impact the pH or salinity. It's not a soluble salt. And so if ash is salt or if ash is sand, I don't care. I got plenty of that. Now, if that ash is alkaline earth metals, sodium, potassium, calcium, magnesium, then I care a lot more. And so I want to know total ash, but more importantly, what kind. And so if I've got ash somewhere in the 10, 20%, I'm not going to put that down on a soil until I know what impact it's going to have on electrical conductivity and pH.
Great. Let me jump to Chuck. Chuck, I think you can hear me even though you're not visible. There you go.
Yeah,
so a question you answered in the chat was how receptive are municipalities to the use of biochar? I think that's a very important question, along with differences of quality in biochar for stormwater applications or urban applications.
So the question is now how receptive they are?
Yeah.
It depends on the agency, and also if you have a champion in the agency. and then look to see how long that person's going to stay with that agency because they seem to move, obviously, with administration changes and elections, and also retirement and things like that. So we've, in the Mid-Atlantic region, I've been at this since probably 2010. We've had a number of champions from the EPA to grant funding with different nonprofits and things to try to move this along. But generally speaking, it's still an educational component to regulatory agencies, particularly permitting agencies, where they look at the book and they say, well, this is the BMP or this is the practice you should use, and here's the standards. And when you start changing the standards, that kind of throws the wheels off their cart. So that becomes a challenge. Where you get your best success is when you're working on projects, at least for me anyway, that you're design build, performance-based, mitigation, like conservation, finance, banking type projects. So there's ways to kind of get it into projects that demonstrate. And then, of course, it's like what Tom and I are working on is get with the academic community to try to get them to recognize the value of biochar, which we're doing in the Chesapeake Bay region right now. So yes, for that component, that's it's a work in progress.
Well, that's good. Thanks, Chuck. We're going to have to wrap it up. I think there are a number of questions in the question and Q&A that you should look at, and hopefully the speakers will respond to. One in particular having to do with yield, but we're going to move on into, since this is going to finish up, into networking. So the next hour will be networking. And as Kathleen suggested, we'll be expanding the number of rooms for that chat as opposed to the lounges. So take your pick, and hopefully we'll get back to you with the answers. And thank you all three for excellent presentations.